Today, we're going to demystify a total classic from the physics lab, the Metre Bridge experiment. We're going to walk through step by step how you can use this pretty clever device to figure out the resistance of a totally unknown wire. So let's get right into it. So here's our game plan. We'll start with the what and the why. What is a Metre Bridge? Then we'll get hands-on and actually put the circuit together. After that, it's the main event, finding that all-important null point. From there, we'll dive into how to record and calculate your results. And finally, we'll wrap up with some crucial tips to make sure your measurements are absolutely spot on. All right, first things first. What exactly is this device we're talking about? Let's break down what it does and, maybe more importantly, the really cool physics principle that makes the whole thing work so well. At its very heart, the Metre Bridge, which you might also hear called a slide wire bridge, is all about precision. It has one single, focused job: to find the unknown electrical resistance of a wire. It's just a perfect example of a simple tool that gives you incredibly effective results. Okay, so the secret sauce here is something called the Wheatstone bridge principle. The best way to think about it is like a seesaw. The circuit has 4 resistors. When the ratios of the resistances on both sides are perfectly matched up, the bridge is balanced, and that means zero current flows through the little detector in the middle. This balance point is everything because it lets us calculate the mystery resistance using the values we already know. That's the principle we're about to see in action. All right, enough theory. Now for the fun part. Let's get our hands dirty and actually build this circuit. It's time to turn that drawing into a real working setup. This diagram, this is our blueprint. Let's just quickly point out the key players. Over in the left gap, we've got the resistance box. That's our known resistance, R. In the right gap, that's where our mystery wire goes, the one with the unknown resistance, X. That circle with a G in it, that's the galvanometer, our balance detector. And of course, the battery, E, which powers the whole thing. Putting this together is actually super straightforward. Step 1, pop the resistance box, R, into the left gap. Step 2, put the unknown wire, X, into the right gap. And hey, make sure it doesn't loop back on itself. Step 3, the galvanometer gets connected between that central terminal and the jockey, which is our little sliding contact. And finally, step 4, connect your power source to the 2 ends of the main bridge wire. And that's it. Your circuit is officially ready to go. With our circuit all set up and ready, it's time for the most critical part of the whole experiment. We're going hunting for that perfect balance point on the wire. Now, before we really start searching, we need to do a quick little check to make sure all our connections are solid. Gently touch the jockey to the 0 centimeter end of the wire. The galvanometer needle should swing to one side. Now do the same thing at the 100 centimeter end. It should swing to the opposite side. If you see that happen, congratulations, your circuit is working and that null point is hiding somewhere in between. So what is this null point we're trying to find? It's that one specific spot on the wire where, when you touch the jockey to it, the galvanometer needle doesn't move at all, not a twitch. That's our null point. It's the physical proof that our Wheatstone bridge is perfectly balanced, and it's the absolute key to our entire calculation. And here is a massive pro tip for getting a really accurate result. You should always try to find your null point somewhere near the middle of the wire. Why? Well, it just minimizes the percentage error in your length measurements. So what you do is you adjust the known resistance R from the resistance box until your null point lands in that sweet spot, ideally somewhere between 45 and 55 centimeters. Awesome, you've found the null point. Now it's time to put on your scientist hat. We're going to document what we found and let the numbers tell the story. Look, any reliable experiment needs more than one reading. So for each try, you're going to change the known resistance R and then find the new balancing length L. The key is to record your data systematically in a table, just like this one. It makes sure your final result is a solid average, not just a single measurement that could have been a fluke. So, how do we turn those lengths into our actual answer? We use this beautifully simple formula. The unknown resistance, X, is just equal to the known resistance, R, multiplied by the quantity 100 minus L, and that whole thing is divided by L. Let's make this real for a second. Let's use our first set of readings from the table. We plug in 2 ohms for R and 41 centimeters for L. So X equals 2 times, 100 minus 41 is 59, divided by 41. You run the numbers and you get 2.87 ohms. It really is that direct. And finding the resistance is often just the beginning. The value of X you just found can then be used to find a really fundamental property of the wire's material itself, its resistivity, which we show with the Greek letter rho. This does mean you have to measure the wire's diameter, d, and its length, l, but it all starts with the x we just found. Okay, we've got the theory, we've got the method. Let's finish up with the things that separate a pretty decent result from a really great one. We're talking about precision and how to avoid common errors. To make sure your results are legit, these precautions are just non-negotiable. First, double-check that all your connections are tight. Loose ones add unwanted resistance. Second, avoid parallax error when you're reading the scale. That just means looking at it from an angle. Look straight down at it. Third, and this is a big one, don't drag the jockey along the wire, just press it down gently. Dragging can actually change the wire's thickness. And finally, only have the power on when you're actually taking a reading. Leaving it on heats the wire up and changes its resistance. So remember, key in, find your point, and key out. And you also have to be aware of the potential gremlins in the system. If the meter bridge wire itself isn't perfectly uniform, then our whole resistance to length ratio gets messed up. Loose screws, dirty plugs, all these little things can add tiny, unpredictable bits of resistance. Even the copper strips at the ends have a little resistance, and that can throw off your readings. And that leads me to a final, really important question for you to think about. What happens if you physically swap the positions of the resistance box and the unknown wire? How would that change your null point? I'll leave you with that one because not only is it a great way to test if you really understand what's going on, but it's also a professional technique that's used to cancel out some of those errors we just talked about. Try it out next time you're in the lab and see what you discover.